Today we are performing a technical and economic diagnostic on our 5% Lignite initiative. While this project is started as a way to lower the fuel cost, our data show a major value leak in our process. And we are seeing a massive thermal penalty and a projected financial gap also over the if we evaluate it annually. So instead of saving money, we are actually increasing our OPEX and risking the operational problems like failures and high slag viscosities. So in the subsequent slide, we are going to have those profit versus reality of loss. So on the surface, coming to this slide, where on the surface blending 5% cheaper lignite looks like a win because it saves around 67 rupees per ton of hot metal in raw material cost. However, the systematic reality is different because our furnace relies on thermal equilibrium and a replacement efficiency. So lignite's physical property causes a chain reaction of gaps. So when you add up the male choking due to the higher moisture, the raceway quenching, as it is pretty difficult when the this 5% material are blended with a normal conventional PCI is coming to the launch tips, having got a same moisture as the normal PCI, and which leads to a quenching effect and extra coke we have to burn, which result in a net loss of a money for every ton we produce. So the now further to the diagnostic part. To understand this loss, we have to look at three failure nodes. That is, node one is at the coal preparation plant. So this is the first, where moisture causes sticking and a 20 to 25% drop in the mill capacity. Whereas node 2 is concerned, node 2 is the raceway where the moisture dissociation creates a thermal energy penalty of about 24,000 kilojoule per ton of hot metal. And finally, this is no, and finally the node 3 is the deadman zone where the alkali condensation form escapes and block the gas flow. So let's look at this in detail one by one. So coming to the node 1 in our this slide, which is talking about the grindability trap in the coal profession. So in coal preparation, we have fallen into a grindability trap. Lignite is naturally tough and greasy. So when moist, so unlike our brittle bituminous coal, high moisture lignite resist fracture and stick to the grinding mill. So these create a choke zone between 15 to 22% moisture as shown in our HGI curve diagnostic. The result is a 20 to 25% reduction in total mill capacity and a significant increase in the power needed to dry this coal. So this is pretty well nicely explained. So coming to our note 2, failure note 2 about the raceway thermal quenching, and here moving in raceway the 5% lignite blend act as a endothermic anchor, and the residual moisture in the lignite react with the carbon to form um, due to this presence of moisture, the dissociation is taking a lot of energy, and as it strip approximately 24,000 kilojoule per ton of hot metal directly from the furnace. To stop this quenching effect and maintain our flame temperature, we are forced to increase the hot blast temperature or use expensive oxygen enrichment, which kills our initial fuel saving, and at the same time our cost also go on increasing. So coming to the ripple effect, which is about the replacement ratio penalty. So the primary driver for PCI is replacing expensive coke with a cheaper coal. This is our the principle of the economic hot metal production. However, because lignite quenches the raceway and has lower carbon density, its replacement efficiency is poor. Our standard coal has an RR of 0.95, that is replacement ratio, but the lignite component, if we talk about, then it's coming to 6.5. This drop our composite blend of RR, if we calculate throughout, then it's coming to around 0.935. This means for every ton of hot metal we are forced to burn an extra 3 kg of premium metallurgical coke just to keep the furnace stable. So now coming to our failure node number 3, which is about the operation risk and the furnace permeability. So as we know, beyond the thermal laws, Lignite's as chemistry is a bit alarming. It drives alkali like and to vaporize in the raceway and condense in the cooler deadman zone. This alkali cycle weakens our coke and promote the formation of scab and scaffold on the wall as the deadman zone clog with the fines and the scab. Gas flow is strangled, risking severe furnace stability, hanging and sleeping. So coming to our financial synthesis about the true cost of blending. So let's look at the final profit and loss. So we save 67 on the coal itself, but because 3 kg coke penalty we just discussed, we spend an 99 on coke. This leaves us with a definitive operational deficit of 32 per ton of hot metal, 32 rupees per ton of hot metal. So keeping in this mind, that doesn't even include the unquantified overhead like increased mill maintenance or the extra power for drying and oxygen enrichment. So if we come to our final recommendation after so much analysis, so our final recommendation is clear. We must not proceed with a 5% lignite blend. It's not technically sustainable or economically viable. The small upfront saving are totally erased by the capacity loss in the coal preparation, a massive thermal penalty in the raceway, and a structural penalty in the coke consumption. So we must immediately halt this type of initiative to protect our furnace permeability and restore the baseline profitability.